Alright, ladies and gentlemen, here it is, the moment we've all been waiting for, the mole. So undoubtedly you've heard about this from anyone who's taken chemistry before, and they will tell you that this is the hardest concept in the entire world. And actually, as it turns out, they're right. This is the hardest concept in the entire world, but the good news is, once we get this down pat, that means you now understand the hardest concept in the entire universe. And once you understand that, the rest of your life is going to be a piece of cake. And that's what I'm here for, to make your life simpler. The mole, in this case, is not a fuzzy little animal that lives under the ground and destroys gardens. It's actually a counting unit. So we know some other counting units, and those won't be too tricky for you. So a pair. How many is a pair? Well, it's 2. A trio is 3. A dozen is 12. A gross is 144. If you didn't know that, a gross is a dozen. So if I were to tell you I've got a pair of shoes, you would know, hey, he's got 2 shoes. If I were to say I've got a dozen cars, you would say, hey, that guy's got 12 cars. And if I were to say I have a mole of something, you would realize, hey, he's got this many of whatever it is. And that would be 602 sextillion. A very, very large number that we use in chemistry. And we use it because when we count a number of particles of something, it's going to be a large number. If I've got a glass of water, inside that glass are going to be H2O molecules, and there's not going to be 10 H2O molecules or 100 or even 1,000, a million, or billion. There is going to be a lot more than that. There's going to be something along the order of this many. So rather than every time saying, hey, I've got 602 sextillion water molecules, we just say things like, I've got 1 mole of water molecules. Do the same thing with eggs. Rather than saying I want 12 eggs, we just say I want 1 dozen eggs. So the mole is just a counting number to make our lives a little bit simpler when we're dealing with really, really large numbers like we do in chemistry. And this number right here would be written in scientific notation, rather than to put all those zeros and just run into mistakes, 6.022 times 10 to the 23rd. Okay, so remember this number. This is going to be an important number. Might want to put it in our useful information area because we're going to be using it constantly this semester. 1 mole is 6.022 times 10 to the 23rd of whatever it is that we're talking about. And this number right here is actually named after a scientist who came up with it. The scientist who came up with its name was Avogadro. And so this is called Avogadro's constant, or Avogadro's number. 6.022 times 10 to the 23rd. The ironic part is Avogadro came up with this number and scientists laughed at him. They didn't really even know that atoms existed at this point, and so they just kind of brushed him aside. And then he died, and then a couple of years later they discovered that he was right, and so they named it Avogadro's number, even though they laughed at him and he ended up dying before they even verified it. And something else I want you to recognize about this number is it's 6.022 times 10 to the 23rd per 1 mole. Did you catch that? Per 1 mole? What does that sound like? Yeah, that's a conversion factor, ladies and gentlemen. So this is where the mole and dimensional analysis meet. Avogadro's number is a conversion factor. So when we want to figure out how many individual atoms or molecules there is in something, we would find out what 1 mole is and then convert it into atoms or molecules. And we can throw anything on these conversion factors. So 1 mole of eggs, for example, would be 6.022 times 10 to the 23rd eggs. Or 1 mole of bricks would be 6.022 times 10 to the 23rd bricks. Doesn't matter what the object is. If you have a mole of it, you have 6.022 times 10 to the 23rd. Just like if I had a dozen bricks, I would have 12 bricks. If I had a dozen atoms, I would have 12 atoms. If I have a mole of atoms, I have 6.022 times 10 to the 23rd atoms. And more often than not, we're not going to be talking about eggs and bricks. We're going to be talking about atoms or molecules. Yeah, both of those are what we're going to convert moles into, atoms or molecules. And remember, atoms are just a single element, and molecules are compounds. And so if we just have a single element like sodium or potassium or iron, that's an atom. But if we have a couple elements joined together like iron and oxygen, iron oxide, or sodium bromide, that's a molecule because it's composed of elements. And it doesn't matter if it's an atom or a molecule. 1 mole of atoms is 6.022 times 10 to the 23rd. 1 mole of molecules is 6.022 times 10 to the 23rd. It doesn't matter that hydrogen is the lightest element and like uranium is a super heavy element. If we have 1 mole of hydrogen or 1 mole of uranium, we have 6.022 times 10 to the 23rd. I think the thing that throws the most people is the whole mass aspect of this. So when we talk about something as counting units, we wind up with the same number, but the mass is different. And that can sometimes be tricky for people. Let's do it with a dozen first. So if I have a dozen cookies, a dozen Oreos, the mass is going to be about 168 grams. If I have a dozen cars, that's 12 cars, which is going to weigh about 22 million grams. Now, does that shock you that 12 cookies weighs less than 12 cars? No, it probably shouldn't. And a dozen magnesium atoms, so if I had 12 magnesium atoms, it would only weigh this much right here. So a very, 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 very small number. Now, the kind of stumbling block that students run into is they say, wait a minute, you've got 12 of both. They should weigh the same then. If you've got 12 of this and 12 of that, 12 is the same number, and so the mass should be identical. No, the mass isn't identical because the mass per piece is different. And so a dozen cookies would weigh less than a dozen cars. A mole is the same way. So if I have a mole of cookies, I have 6.022 times 10 to the 23rd cookies. That would weigh about 8.43 times 10 to the 23rd grams. So it'd be really heavy. That's a lot of cookies. A mole of cars, how many cars is that? 6.022 times 10 to the 23rd. Avogadro's number again. The mass of that would be an even larger number. A mole of magnesium atoms is 6.022 times 10 to the 23rd. And so you're going to notice all of them have the same counting number, but they all three have a different mass. And so a mole of magnesium atoms, we can now see that we're getting into a range that we can visualize. That would weigh 24.3 grams. So do me a favor, pull out your periodic table and find the box for magnesium. You see it? Okay, look around on it, kind of explore, see if there's anything that looks familiar on there. Do you notice the atomic mass of magnesium happens to be 24.3? So 1 mole of magnesium atoms, that's exactly 6.022 times 10 to the 23rd magnesium atoms. If we were to put them in a beaker, it would weigh 24.3 grams, which just so happens to be the atomic mass. Think it's designed that way? Actually, it is. So before we were calling that number on the periodic table the atomic mass, another way it's referred to is the molar mass. And so it's the mass of 1 mole. Once again, the periodic table is to the rescue. So sodium, for example, has a molar mass of 22.9898. We'll round that up to 23.0. And that's how many grams 1 mole would weigh. And so the units of this then would be grams per mole. So 23.0 grams per mole. What does that look like? If you said conversion factor, you are absolutely correct. So 23.0 grams of sodium is 1 mole of sodium. And of course, 1 mole of sodium is 23.0 grams. It doesn't matter, both these mean the same thing. You would just pick the one that's going to cancel the units that you want you to cancel in dimensional analysis. Now, hey, I know a bunch of you are probably noticing I'm writing mole as M-O-L. That's shorthand. Just like for grams, we use a G. For mole, for whatever reason, the shorthand for it is just to drop the E. However, do not, absolutely do not use for mole M. Okay, M means something else. M means meters, and so we don't want to write something like 1 m of sodium, because that would be 1 meter of sodium, and 1 meter of sodium does not weigh 23 grams. Okay, and same thing with iron. So iron, which is about 55.8, and that would be 55.8 grams per mole. And likewise, we can write that in dimensional analysis form. So 55.8 grams of iron would be 1 mole of iron, or 1 mole of iron, 55.8 grams of iron. And I want you to notice right now that 1 mole of iron, 1 mole of sodium, they weigh differently. It's because iron is larger than sodium, and so we'd have a different mass. Does that mean we have more iron atoms in 1 mole? No, we do not. We have 6.022 times 10 to the 23rd, and we have 6.022 times 10 to the 23rd. Well, then why do they weigh different? Because a single iron atom is larger than a sodium atom, and so they wind up with a different mass, even though it's the same number of atoms. Okay, we can do the same thing with molecules as well. So let's do potassium nitrate, ammonium oxide, and diselenium trisulfide. So potassium nitrate first. So potassium is about 29.1 grams per mole, nitrogen is 14.0 grams per mole, and oxygen is 16.0 grams per mole. And we also notice that we have 3 oxygens, and so if we want to get the mass of this entire compound, we'd have to take into account the fact that there is 3 oxygens, and so we're going to multiply the oxygen by 3. So we're going to take those 3 masses, add them together, of course multiplying the oxygen by 3, and that'll give us the total molar mass for this compound. And then we get a total mass of about 91.1 grams per mole. And so what that means is if we have 1 mole of potassium nitrate, so 6.022 times 10 to the 23rd potassium nitrate molecules, it would weigh 91.1 grams. And then ammonium oxide, which is NH4, and we need 2 of those to balance out the charge of the oxygen, which is 2 minus. And so nitrogen 14, hydrogen 1.01, and oxygen is 16.0. So then numbers here, you notice how we have the parentheses with a 2 on the outside. That means we have 2 ammoniums. And if we have 2 ammoniums, that means that we're going to have 2 nitrogens. And so nitrogen's mass would be times 2. And it also means that we have 2 H4s. And so we have a total of then 8 hydrogens. And so we need to multiply that mass by 8. And so then with significant figures, we get a total mass of 52.1 grams per mole. And that would be then the molar mass of ammonium oxide. Okay, why don't you try that last one by yourself, diselenium trisulfide, see if you can write the formula, and then turn the formula into a molar mass. Okay, so we've got 2 seleniums and 3 sulfurs, and so when we put those 2 together, we would get a final molar mass, 254.2 grams per mole. Okay, so we learned 2 things in this video. First one is that 1 mole is 6.022 times 10 to the 23rd. It doesn't matter what the object is. If you have 1 mole of it, you have Avogadro's numbers worth. Also, if you have 1 mole of a particular element or compound, it's going to be equal to its molar mass, and that's in grams. Okay, and the molar mass is going to be different for each particular element compound, and so 1 mole of that element or compound is going to weigh different than another one. And these equals, instead of saying equals, why don't we say per? Because that helps us remember that these are really conversion factors. So if we want to convert from grams into moles, we would use the molar mass. If we wanted to convert from number of atoms into moles, we would use Avogadro's constant. And we can also go from molar mass all the way to the number of atoms or molecules. That's what we're going to show you how to do in the next video.